Hello everyone. Welcome to this session on working with raster data in QGIS as part of the online training program on Introduction to Remote Sensing and GIS using QGIS. Till now we had sessions on basics of remote sensing, GIS, QGIS, working with delimited text data, vector layers in QGIS, and preparation of basic map, georeferencing of scanned maps in QGIS, and also we have seen how we can make use of high resolution satellite imagery for mapping of irrigation assets or creation of vector data using digitization tools. In this session, we will start working with raster data. You have already started working with raster data, but in this session, we will see some very basics uh, right from how we can download sample raster data, how we can add raster data to QGIS, how we can change symbology, do visualization, and how we can make use of raster calculator for doing band math, etc. Raster data is generally used to display information that is continuous across an area, for example, elevation information, rainfall, and other hydrological parameters. In case of vector data, as you have seen, attributes remain the same for the whole feature or features. Therefore, it cannot be used for representing non-homogeneous features which vary from place to place. For example, natural vegetation varies in terms of predominant species, in terms of health of the vegetation, etc., from place to place. And if you try to or attempt to digitize for capturing every variation of vegetation to create a very good vector data set, it will consume lot of resources and time. And if you try to simplify things by marking contiguous forested area as one single polygon feature, then you will be losing information in the process. Therefore, raster data in the form of gridded pixels can be used for representation of um, or display information which is varying continuously depending upon the computational resources, depending upon the amount of the input data. You can have very finer resolution pixels, smaller pixels to represent the information or real phenomena of the world. The raster data can be used, can also be used as a backdrop behind the vector layers for preparing maps. Sources of raster data we have seen are satellite and aerial remote sensing imagery, scanned maps, and also if you have point data which is collected from through a very good network of observation sites, then you can use interpolation techniques to generate raster data. Rasters are good for depiction of real world surfaces in the form of images, but also abstract ideas, say for example population density, air pollution parameters, etc. Now let us start working with raster data. First we will download sample raster data which we will be using for this session. We have suggested to create login IDs for some of the data sources that we have shown in the session on open access datasets. Even otherwise, we will be providing the sample exercise data for which will be used in this session. So for this session, we will be downloading SRTM DEM tiles and then Landsat 9 multispectral imagery and LULC data, NRSC LULC data. So let us start. SRTM DEM data is available at 30-meter resolution. Uh, it was collected in the year 2000. It was generated like before going to the data download. Let us look at some information about SRTM. SRTM is Shuttle Radar Topography Mission. In the year 2000, from February 11 to 22, it took measurements and then the radar data, it was used for data was collected in X-band radar as well as C-band radar during the number of passes during this period, and then it was used for generation of digital elevation model. Now remember, digital elevation model is always a generated data set. It will never be 100% accurate, uh, and any pixel, if it is 30 by 30 resolution data set, that means we can consider it as an average elevation. The value of elevation which is stored in that pixel is the average elevation of that pixel, and that there will be an error of plus or minus 2 meters. In this case, they themselves specify. So SRTM DEM can be used for purposes such as basin delineation, or at any other contour generation of contours at district or basin scale, sub-basin scale. But if your application is something specific to local level, like alignment of canals or contours at the local level, um, so in that cases you need to have a high resolution DEM, which you can get through LIDAR survey. At basin and sub-basin level, basin delineation, all these open access data sets like SRTM. Now we have Copernicus 30 meter DEM, which is latest, which is from European Space Agency. In the Bowen portal, we have shown in the open access data sets how to download Bowen Cartodem DEM tiles. It is also available at 30 meters. Now it will be very useful for hilly states of northeast like Arunachal Pradesh, where these open access data sets, SRTM data sets, global data sets, have a lot of no value data, which so we cannot make use of SRTM for basin delineation. We can make use of Cartodem in such cases, and there is also Aster DEM is also there. So anyway, let us come to data download. Yeah, once the data was collected and the DM was prepared, and later on it was improved upon, like it was there are many versions, version 1, version 2, version 3, version 4. They tried to fill the voids every time when DEM is generated. At the time of data acquisition, there will be some errors, there will be effects of shadow or no data, there will be artificial voids or artificial sinks, and you need to if you go before going for basin delineation, which we will be doing in subsequent session, we need to fill those sinks, artificial sinks. Otherwise all the water will flow into the sinks. That is known as hydro processing, that we will do separately. Now what some people have done is they started giving void free data set, void free SRTM DEM. Globally is available at 90 meter resolution. So we will download that data set from a portal, this one, srtm.csi.cgiar.org. It doesn't require any login to download data. If you want to download the original for basin delineation, it is always better to go to the original 1 arc second or 30 meter resolution data set, which is available at USGS Earth Explorer, and download the tiles, do the mosaicing, and then start doing filling of sinks and other steps of hydro processing. Now here we want to just show you how we can work with raster data. We are going to download SRTM data. You go to this website, srtm.csi.cgiar.org, and then click on this SRTM data tab. Then you see SRTM data is available in such tiles, 5 by 5 degree tiles. Now tiles are different from spatial resolution. Spatial resolution will be 30 meter, or here in this case it will be 90 meter pixel size, but these tiles are made available as 5 by 5 degree, means approximately 5 into 110, 550 by 550 square kilometers, which is good enough for one tile will cover a big area. And then it is also available at 30 by 30 meter tile. So, and format is GeoTIFF. We will download 5 by 5 degree tile. Uh, we will download it for Pune region. So I know the region now. This is, you can see it is these are the tiles for peninsular India. This is like a world map. Um, Now I think this is the tile which will cover Pune region. We can search that. We can have a look. So click on search, and you can see uh, this covers western coast of Maharashtra and also Deccan Plateau, some portion of the Deccan. And every tile, like you can see, SRTM 90 meter digital elevation model version 4. So every tile has one numbering system they have. So extent. So you can download it. You can click on download SRTM. It doesn't require login. So it is getting downloaded. So let it happen. Let us come to our second data source, Landsat 9 multispectral imagery. We have seen in case of India, we have Bhunidhi portal, wherein you can download list 3, list 4, all those data sets. They are multispectral imagery. Similarly, there is Copernicus data space ecosystem for downloading Sentinel data. Sentinel-2 is multispectral, Sentinel-1 is radar data. Now, for Landsat, you can download it from Landsat is multispectral. Landsat series is available. Landsat is a program which was initiated in the year 1972. So it is the longest series of Earth observation data available in the world, and data is made freely available. Resolution is 30 by 30 meters. So after Landsat 1, there were other missions, Landsat 2, 3. Some missions failed. Some they have run out of life. Now as on date, Landsat 8 and Landsat 9 are operational. And they have a plan to launch Landsat next mission, which will be at higher resolution and with a lot of scientific products. But now we have to see when they will be going to launch, as there is some issue with the support in US. Anyway, let us check this. USGS Earth Explorer. You search for USGS Earth Explorer in Google and go to this website. Hope you have created your login. For searching data, you don't require login, but for downloading data, you require the login. Yeah, I have already logged in previously. So how we can download the data? You can go to world features here in the under search criteria tab. Enter search criteria, world features, and you can search for Pune here. Or another way is you go to this selected geocoding method, go to address or place. In case if you know the Landsat tile path and row, because Landsat is collecting the data as it flows in its orbit. It for every location will be the imagery will be collected after every 16 days. Landsat 8 after 16 days, Landsat 9 after 16 days. So if you know the path and row for your location, you can go and download. You can go to Landsat page and see the path and location of different regions. So anyway, here we will be searching by address. Like I will search by Pune. Click on show. You can see in the result you have Pune, Maharashtra. Address, if you click on this this link, it will take you to the location. You can change the base map here. here now it is ESRI vector map. You can go for ESRI you can go for topographic map or world imagery. Yeah. So zoom into the location. Now this is Pune. Now you see this is a very high resolution data for visualization purpose they have provided. Most likely it is a proprietary, maybe QuickBird or Airbus. There are companies which provide you sub-meter resolution data. It is one layer, just one layer. Whereas Landsat 9, Landsat, these are series of data set. Every 16 day you get, and the resolution is 30 meters. So yeah, you decide the extent. Anyway, our Landsat tiles are big enough. Each tile, depending on the swath, it is whole Pune region will come under one tile. So once you chosen your area of interest, you can create. You can even upload shapefile here, but we are making use of the map. So you can click on this use map. Even you can search with this point location or the Landsat tile which is intersecting with this point. Let us do that. Otherwise, what you can do is you can if your area of interest is big, like for SRTM, if you want to download SRTM tiles for delineation of a big river basin, you may have to download multiple tiles. So for that you have to zoom into the your area locations. Like for example, say this is Kadakwasla Dam. This basin will be, even in Kadakwasla Dam, the tile will be there. It may be covered by only one tile. But if you take a larger basin like Krishna Basin, then it will be covered by multiple SRTM tiles. So then you can create polygon. First you can create, if you click on use map, it will create a bounding box of a rectangle. You can then drag these points and then create your area of interest. Then it will, all the tiles which are intersecting with this area, you will see in the results. Or you can create a polygon by adding more points. So for our purpose, we'll remove this. Again, I will go to single point and then click on data sets. Then it will take you to the second tab of data sets. We are looking for Landsat. You can see Landsat collection. Yeah. Earlier, Landsat all imagery used to be in collection 1. Now they have improved the collection, and they are releasing imagery in collection 2. Earlier it was collection 1. Through some algorithm they have tried to refine the imagery, and now all the collection is kept in collection 2. So you should be aware of these terms: collection, tier, and level. Regarding level, level 0 means raw satellite imagery. Just like you have taken a photograph from the top of atmosphere in using spectral sensors, then it is level 0 product. There will be digital numbers in that, and then it can be converted into top of atmosphere reflectance or atmosphere reflectance using some formula. So level 0 is raw data. Level 1 imagery means it is top of atmosphere reflectance after doing geometric corrections of those things. And then if you remove the atmospheric disturbance, then you will get level 2 product, that is surface reflectance, which is the sensor is only observing the top of atmosphere reflectance. But if you want to do the identification of feature based upon its signature, you have to remove this atmospheric disturbance, for which there are algorithms. There may be because of the atmospheric constituents, there will be lot of absorption and other because there may be presence of haze, all those things you can remove, and then you will get surface reflectance, which you can, these products, level 2 products are surface reflectance, which you can use for land use land cover mapping. And level 3 products are scientific products for specific themes, like they using landsat data they have created uh, water body products after mapping water bodies. Such products are science products, like you can see here, Landsat 3 science products level 3. You have burnt area, dynamic surface water extent, fractional snow cover area in each pixel, and FSCA statistics. These are all scientific products. Then level 2, these are surface reflectance products. Level 1, these are top of atmosphere reflectance products. So we will select this. You can see Landsat. Check this box of Landsat 8, 9. OLI, TIRS are the names of the sensors on board Landsat 8 and Landsat 9. Collection 2 and level 1 product. You can see Landsat 1 to 5, 4 to 5, 7, 6 I think was a failure. These are available here. You can search all the archive here. Then once you decided your product, you can click on results. Then it will populate all the Landsat tiles which are intersecting with your point of interest. And there are about 372 tiles. That means from the beginning of Landsat 8 and from the beginning of Landsat 9, all the tiles are shown here. The latest tile, see in case of Landsat 8, it is from 28th October 2025. This is naming convention. Landsat LC08 means Landsat 8, L1 level 1 product, and then here 2025 1028, that is from 28th October. Date of acquisition also it is given here, 28 October. Path is 147, row is 047. As you can see, path and row are same for all the imagery as far as Landsat 8 is concerned, and even Landsat 9 is also, it is the same. So Landsat 8 imagery was from 28th October. Landsat 9 imagery, latest imagery, is from 4th October. 4th, after 4, the next image will be on 20th. Maybe there is some lag. And in this case, after 28th October, the next image will be after 16 days. You can check the footprint. This will be the tile, like the satellite flows in this direction and it is collecting imagery for this region. So always Pune is covered by one single tile. You can download it from here. You can also do further set additional criteria before going for results. You can say go to additional criteria under Landsat 8.9. You see you can filter by cloud cover. You can filter by date range. Say date. The additional criteria, let us select date range. Say we want clear images without much cloud cover. We can go for the month of February, say 2024, February 1 to 2024 to 28. Okay. And then you look for the results. Then you will have limited number of tiles, as you can see. Landsat 8, this is Landsat 9 from February 20th, 12th February, Landsat 8. 4th February. You see the number of temporal resolution is 16 days. After 4th, you have on 20th. Similarly, in case of Landsat 8, after 27th January, it is 12th February. So we will select this Landsat 3 9 20th February imagery and click on download. For that you need to log in. Now in the download also you have the options of to download all the entire all the bands. All the bands now we may not be required. So if you see Landsat download, you can click here and download all the bands, or you can select files. Like these are all the items which are available. These are the multispectral bands B1, B2, B3, B4, B5, B6, B7 up to B11, and then there are some quality bands which can be used for filtering clouds, some information about presence of clouds, etc. There are many things which will be useful. Now we will only select multispectral bands, say B1 to B7. And then, now what are these B1 to B7? You can check in the Landsat 8 or 9, both have same bands. Landsat 9 bands, that is such, right? So Landsat 9 has 11 spectral bands. Band 1 is coastal or aerosol, band 2 is blue, part of the electromagnetic spectrum, green, red, near infrared, band 5, shortwave infrared, band 6, shortwave infrared 2, band 7. Then panchromatic 8 and cirrus 9. Even 9 is not a multispectral. It has information about cirrus clouds. So we have decided to download from B1 to B7. Even B1 is not much useful for our purpose. It has its own applications. This is the range of the wavelength electromagnetic spectrum. Then you can see B10, B11 are thermal bands. These are OLI sensor, TIRS sensor. So same is the case for Landsat 8. Download, click on download selected now. Okay. So you can see the download is happening. Each band is about 90 MB. All of these are raster images. Close. So, and third data set that we want to work is LULC data. In case of India, now LULC is again a generated data set like DEM. NRSC generates annual LULC maps and images, and they have a system of LULC classes. They at 3 levels, I think they generate it. They use AWIPS data, which is at 56 meter 56 meter resolution for creation of LULC data. So this data set is available for download from India Varis portal. You can check the same portal which we have seen for downloading administrative boundary layers. Now we are going to download raster data. Go to data download and then geospatial data. Go to LULC, land use land cover. Yes, click on discover data. So it is from NRSC, which is an implementing agency of under National Hydrology Project. Any information may be sought from the producing agency. Okay, let us download for latest year, which is available here is LULC scale 250K for the year 2020, 17 and 18. Click on download, and you have to give your like not credentials, you specify the purpose and give your name and email. There is no login that is required, and click on submit. Then it will also download. So that's about the data sets which we will be working upon in this. Now let us add our raster data which we have downloaded. You very well know how to add any layer in QGIS. Go to layers tab in the main menu and then add layer, and now you have to select add raster layer. Alternately, you can go to this icon of open data source manager in the data source manager toolbar, and then you have to go to the tab of raster, and then you browse your file and add. There are other ways, like you can if your browser panel is active, you can simply drag the file from the browser panel by browsing it here and then dragging it to the layers panel. You can even simply drag the file if it is readily accessible. Say if we have just downloaded the LULC raster from the India Varis website for the year 2017-18 at the 250,000 scale. If I drag, I can drag it simply. This is a zip file. This is not a single file. I can drag it. Because it is a zip file and it has multiple auxiliary files along with the actual raster, it is asking me to what items to add. Otherwise, normally the raster file will be a single file, unlike the shapefile. And .tiff, whenever you see .tiff extension, it is the raster file. It is a geotiff file. Just like shapefile is a very widely used format for saving vector data, GeoTIFF format is the widely used format for saving the raster data. There are other formats like .img and other. So you can select this .tiff item to add. And what are these auxiliary files? You will not find these auxiliary files in other datasets, in other raster datasets, but in this specific case of LULC map, which was prepared by NRSC, it has these auxiliary files like tef.ovr, which is basically an overview pyramidal file. Because your LULC layer is at a finer resolution of 56 meter, and you don't want to read or load the full resolution file every time, you can store your different overview levels. Like you can have a low resolution level 1, 2, 3, and like in a pyramidal manner. The same thing that you find in Google Earth. In Google Earth, when you open Google Earth, you will find one resolution. As you keep zooming in, the finer resolution images will come. They will be displayed, and you can go up to the level of field or individual house. Similarly, here also it is saved in different levels. So this file is used for that pyramidal. It is known as pyramidal structure. And there is also one file with .dbf. This dbf file you must have seen in the file, one associated file with extension .dbf. We said it is database file. Now here in this case also, even though rasters don't have an attribute table, they have created an attribute table. This will be generally used for rasters which are categorical. Like here in this case, LULC map, you prepared an LULC map through multi-temporal and multi-sensor satellite data. They are giving the LULC map for whole year, 1 year. For 1 year, they have collected data. They have seen satellite images from different points of time, and at 56 meter they have collected the data, and then they assessed the spectral signature, and then they prepared based upon the spectral signature. They have given one class. There are 18 classes in this classification at 2.5 lakh scale. So every class will be given one number, and in the pixel, in the raster pixel, the class number will be saved. Now, how to know which class is what is the descriptive name of the class, whether it is Kharif class or Rabi class or water body class, that is saved in a DBF file. So that's why we have a DBF file also here. Now we can add .def layer. So this is the LULC map for the year 2017 and 18. 17-18 means water year. Starting from June of 17 to May ending of 18. Now you see we can make use of this tool that we have used it while working with vector data and also delimited text data. This tool is identify features. You click here on any pixel. If you zoom in, you will find the pixel size. This is 56 by 56. You will find pixelated. So you see, as I keep zooming in, different pyramidal level layers are being displayed. The actual raster is this one, the final resolution at 56 meters. So if I select this layer and then I use this identify features and click here, you will get the band. There is only one band here, just like digital elevation model, which we will see. It is not the multispectral band, it is the value of land use land cover 14, and it is given, it is also being given how many count, I think number of pixel count in the overall image. I have to see, yeah, area square kilometers for this class, wasteland class, and we have different levels like level 1, level 2, level 3. It is simple broad class, and then finer like under agricultural class there can be fallow class and then crop land. In the first level will be agricultural land, second level whether it is a fallow land or crop land, and third class can be third level can be cropland, maybe Kharif or Kharif only or Rabi only or three crops or jade. So let us see, let us explore. Yeah, we have to see some cropland. I think this is cropland. Yeah. So you see in this pixel, this is broad class is agricultural land, which is a cropland, and it is a actual class 18 classes. The class number 2 is associated with Kharif crop. So if you want to have a look at the list of these classes, you can even open your database file. Yes, and also generally raster layers are not associated with attributes. Vector layers you find the attribute table, but in this case you have a DBF file. They have created a raster attribute table which you can open by right clicking and open raster attribute table, and this gives you these information, the value of the land use land cover class and broad level 1 class, whether it is water body or agricultural land, forest, and second level you see cropland, fallow land under agricultural land, and plantation. Built up, it has only one class, level 1, level 2, level 3. In case of forest, the broad class is forest, and then under it you have evergreen, deciduous, scrub forest, littoral, swamp, natural. Similarly, under wasteland you have two subclasses, wasteland and sandy land. If you come to the level 3, which is the actual 18 classes classification of LULC, which we are looking at, you have under cropland there are further classification of Kharif crop, Rabi crop, jade crop, double crop or triple crop, current fallow, fallow land, current fallow, and plantation is plantation. So in this way. So if you see this, these are the 18 classes. And also you find that you need not give the symbology here. The symbology is also inbuilt. Like they have defined the style also. In this raster attribute table itself, you will find the area, and then this is the color associated with built up color associated with water body. Generally, we use particular colors for displaying particular land cover land cover classes. So that they have used. So anyway, so in this way you can load your raster data and explore the data. We will try to do some analysis of area and other how much area is occupied by what class, etc., if time permits. That we will do in subsequent sessions. So this session is about working basics of working with raster data. So this is one categorical data which is being provided along with the database file with pyramidal overviews and also symbology. Now let us come to our second data, which is land use land cover, SRTM. Again, I will try to drag it. You can extract the layer. I have extracted the zip file, and then the main file is TIF. You can drag and drop here, or you can drag even the zip file. Now it will be directly added because the TIFF file, there is only TIFF file, and other there are no DBF and other files, other overview layers. So this is our SRTM DEM at 90-meter resolution. Let us also, to just to get the context, in the previous session we have installed this quick map services plugin. Now we will add this, we will try to add Google satellite and OSM standard base maps from quick map services plugin. I hope you all have installed the plugin. In the layer panel, you can double click the layer or right click and select the properties to open this layer properties dialog box, and then you can select the various tabs to look at the layer properties. In the information, you have all the general information, the provider of the layer, then the when the size of the file when it was lost modified, and then the format geotiff and the extent, how many the number of rows and columns and where it is saved on your system, the statistics, the maximum value, the minimum value, and standard deviation about the elevation, and then it will also have the pixel size information, which is 0.00083 degrees. If you convert it into seconds by multiplying into 60 into 60, 1 degree it has 60 minutes and each minute has 60 seconds. It will be about 3 arc second, which is nothing but 90 meters at equator. So this our pixel resolution is about 90 meters. So you can check that, and then you can also check the coordinate reference system. It is in EPSG 4326 WGS 84. Now this this is the global coordinate system. This is not a projected coordinate system where all the coordinates are in the latitude and longitude. The for checking the code for any other projected coordinate system, you can refer to spatialreference.org. We will see that when we try to reproject the layers, we will have a look. Now you can read about the accuracy based on the World Geodetic System WGS for 1984 ensemble, that is the universally accepted datum. It has a limited, but the accuracy is limited to at best 2 meters, and then can also see the number of bands. There is only one band which where the no data value is minus 32,768. The significance of no data value is, if the no data value is specified, then that value, wherever the pixel is having that value, it will not be considered for any kind of analysis. So it will be masked out, right? And then the minimum value and the maximum value for the entire layer, you have these statistics information even here, maximum and minimum values. So in this way you can read the properties, the metadata of the layer. In the source tab, you have a very basic information about what is the CRS, coordinate reference system, and what is the source, where is it saved. And now let us come to symbology. uh, Under symbology, there are three tabs of band rendering, layer rendering, and resampling. We will have a look at how to change the symbology for changing the visualization. Uh, so you can see under band rendering, there are many render types of multi-band color, paletted, unique values, single band gray, single band pseudo color, hill shade, contours. Now by default, if it is a single band imagery, like in this case there is only one band, it is not actually the electromagnetic spectral band, but it is a digital elevation model where each pixel has elevation value, so it is considered as a single band imagery. So by default it is displayed in single band gray. There is only one band. Um, and it is the contrast enhancement. You can see the options available are no enhancement, stretch to min max, stretch and clip to min max, clip to min max. Now let me show you by uh, changing this contrast enhancement to no enhancement. Then and if you click on apply, you see the base layer, you cannot distinguish between the change of elevation. There is no contrast at all. So you can change it back to the, if you stretch it to minimum and maximum value, you will have a better visualization. That is the default option also. So and then what are these minimum and maximum values that are being displayed? The properties of the minimum and maximum values, you can select under this, the minimum and maximum value settings. You can see here there may be very few extremely low and extremely high values present, elevation values present in the layer, which which can have on a negative impact on rendering of the raster. For example, suppose if the one pixel is having a abnormal imaginary height, say 5000 meters, and rest of all pixels are at the level of 100 to 1000 meters, then what happens is, in the gray band scale, the 5000 and above will be represented in white, as a white in white color, and this minimum values and nearby minimum values will be represented in black color. So all the image appears to be in black color. You won't be able to find any contrast. So you can go for absolute minimum and maximum values, or you can go for this option of cumulative count cut, which will remove the outliers, the 2 percentage values. So the values from 2 to 98 percentage of the elevation which are there. So very high values and very low values are removed. Let us check this. Now let me before that, let me zoom to the layer. Now you can see this. Then now let me remove this base map, and there may not be much difference, but in some layers it makes a lot of difference, removal of outliers. So if I select this option and if I apply it, maybe there is not much change here, but you can definitely see the change here. The values that are represented, the low negative abnormal values have been removed. Very high values are also removed. So top 2% and low bottom 2% have been removed. Similarly, you can check for other settings. You can define the values or the range where you want to visualize your data by user defined minimum and maximum value settings, or you can select this mean plus or minus standard deviation to which will again, it is not a proper display. You can see the values between on either side of the median, standard deviation to standard deviation. This is the range. So let us go back to the original min max settings and stretch to min max and then apply. So this is just for enhancing the contrast for visualization. Then you can also see in the symbology, such single band images can be represented in the form of in single band gray, or there can be also another option of choosing the single band pseudo color. Then it will ask you to choose the interpolation method and also the color band, which is important. Now this is an elevation data set. So there are predefined color ramps which are defined for depicting elevation. You yourself can make a color palette for a depiction, or you can make use of the existing uh, color palette. So you can try for you can right click on the color palette, on the color ramp, and select create color new color ramp, and then you select this in the dialog box you select the gradient, or you select the this you want to make use of ready-made color palette, so you can select this option of catalog CPT city and then click on OK. It will open you this color ramp, the predefined color ramps for various categories. There are 1152 color ramps. You can select the topography option and can select the elevation color ramp and then click OK and then apply. So you can see in the background the image has changed, the visualization it has changed. Now here what you can do is you can click on classify. Then you see the lowest values are represented as in this color, and there is a gradual variation from lowest values to highest values, which are in black and are in chocolate color. You can apply. You see there is a you can clearly visualize the water divide here. That is the water divide of the Western Ghats, which separates the all the west flowing rivers. This is the Konkan plain, and all the east flowing rivers will be going on this side. This is part of Krishna basin, and here there are many medium and minor basins of west flowing rivers. So in this way you can change the symbology of elevation layer. There are other options like statistics extent. And there is one more way of accessing this symbology by using this open the layer styling panel in the layers panel itself, where you can make the changes and view the changes happening in the map canvas area. So some options, some common properties of the layers properties dialog which we have seen earlier, are available. And then you can configure the layer styles and view the changes in the map canvas directly. So let us go back to the original layer properties dialog by double clicking and then go to symbology. So we have seen the band rendering, all these options, and then minimum maximum settings, and then in the layer rendering, yeah, in one more thing is in the minimum maximum settings you can also define the extent of statistics. The statistics extent you can define it as whole raster, or you can check it to updated canvas. If you check to updated canvas, so what happens is as you keep updating by zooming in, the automatically dynamically the it is calculating the minimum and maximum for the extent of the canvas, and then it is changing the visualization, which may not be prominently visible here because there is not much variation in the values, but it is happening. Then there in this way there are many options which we can explore for raster symbology. Basically this is only for visualization purpose. Nothing is being changed in the value stored in the pixel, in the each pixel. If you intend to change the values of the pixels, you can make use of raster calculator. Raster calculator allows you to perform calculations on the basis of the existing raster pixel values. In the QGIS, there is more than one way you can access the raster calculator, and in fact, there is more than one raster calculator that is available through various tools. You better go by the tool which is available under raster analysis in the by checking the processing toolbox. Now, in the main menu, you go for this processing and then click on toolbox, and you will find one dialog box of processing toolbox. Here you can search for raster space calculator, and then you will find that there is one raster calculator under raster analysis under the main the core tools of the QGIS. You will also find raster calculator under GDAL under Saga, but you check this raster calculator under raster analysis. That a dialog box will open. Now suppose if I want to create an elevation raster in feet instead of meters. I want to change the values of the elevation stored in each pixel from meter to feet. So then I simply have to multiply the value of each pixel, elevation values of each pixel with a constant that is about 3.28. Now let me you can see this layers. It will populate all the active layers which are in the layers panel, and then if you double click it, you will find that in the expression box you can make use of the values of the pixel values of this layer. Now I have to simply multiply the values of each pixel with 3.28. Now I can now you can just run this, and before running you can also give a reference layer for automated extent, cell size, and coordinate reference point. You can select the SRTM, the your input data set only, and don't do anything else with the other options. You can save the output to file onto the disk, or you can just run. If you are not saving anything to file, it will create a temporary layer, and you will lose all temporary layers when you close QGIS and reopen it. So let me run this without saving. So when it is done, you will get this message immediately. The algorithm is finished and it has loaded the layer. So you close this and you check the layers panel, where you will find a new temporary layer. As you can see, this symbol indicates it is a temporary layer only, and the contents will be discarded after closing QGIS unless you store it to the disk. So the temporary layer by default, it's output of the raster calculator. It is named as output. You can change even the name of this, and you find that as you can see, the values of have been multiplied by 3.28. You can check by using this identify features tool. By selecting by the active layer, that is output, you can click in any pixel and you will find that the value of elevation stored in that layer output is in feet 2584.64. And if you activate the SRTM layer and check the value of the pixel, you will find that the values are in meters. um, so in this way, you can make use of raster calculator. And if you want to save this temporary layer, you can simply right click this layer and then export, and then select save as. You can give a file name by giving the location. I can save it in solution folder. I can simply name it as DEM feet or anything, and the CRS will remain the same, global coordinate system, and then you click on OK. So as you can see, a new layer has been created on the disk, and now you can remove the temporary layer. You can zoom to the extent. It will have the same extent as the original value, original layer of the DEM. Now let us use raster calculator for reclassification of the raster. Suppose you want to uh, uh, mask out all pixels with elevation less than 1000, and you only want to have those pixels whose elevation is greater than or equal to 1000. You want to retain it. So for such masking out areas as per the condition, you can make use of raster calculator. Now let me remove this layer which is not required. I will make use of SRTM. I will also remove these base maps which are not active. So I can again go to processing, toolbox, then under raster analysis I can click on raster calculator. It will open the same dialog box, and in the layers you will find the active layer SRTM. You can double click it. So in the expression, you can make use of it, this values of these layers, this layer. So I have to write an expression. Basically I want an expression which will retain the values wherever the elevation is greater than or equal to 1000 meters, and then um, mask out all the pixels where the elevation is less than 1000. By masking out, you mean you will set it to 0, or you and then you define 0 as the no data. So let me write the expression. So SRTM, wherever the value is greater than or equal to 1000, You put it in parenthesis. You can check whether your expression is valid or not valid. If you are missing any parenthesis and if you are missing any formula, if it is not right, it will show you in red that it is not valid. So this expression, if I run, it will give me a Boolean layer wherever this expression holds true, there the pixel value will become 1, and wherever this expression is not true, there the values of the pixel will be 0. Such a layer where the values are either 0 or 1 is known as a Boolean layer. Now if I let me run this without saving, but however you can provide this reference layer. You can select SRTM as a reference layer, use it for automated extent, cell size and CRS, and then you run this. Fine. So you can see a new layer has been generated. A temporary layer again has been generated where the values are only 1 and 0. You can even check the properties, the statistics of these. The maximum value is 1 and the minimum value is 0. So you can check this layer, zooming to the extent. You can zoom in to check the values using this identify features by activating this output, the temporary layer, and you can click in any of the pixels. So these white portions are those pixels where the value is 1 or where the original SRTM has value of elevation greater than or equal to 1000, and all these black portions are those where the elevation is less than 1000, and in the new layer its value is 0. Now so if I want to mask out these 0 values, what you can do is by masking out, you want to remove these values, these pixels with 0. You don't want to consider them in any analysis. You want to make them transparent, or you want to make it no data. No data will not be considered in the any kind of analysis. So what you can do is you can right click, go to properties, you can go to this transparency tab, and here you can specify the existing no data value is this one, minus 3.4 into 10 power 38, a very small value. You can also add an additional no data value here. You can add 0 value and then you apply it. Okay. So as you can see, in this output you have only one value stored, that is 1. Wherever the value, you can check wherever the value is 1, it is black in color, and outside wherever the value is different from 1, it is become no data. So you have masked out all the pixels where elevation is less than 1000. So you can add the base map. Now let us add from web quick map services. Let me add Google satellite. So here, so these black portions are those areas you can click on the layer to make it active and deactivate again. You can see all those areas, the rich portions and higher elevation values where the elevation is greater than or equal to 1000, they are in black, and remaining portion they are masked out. So in this way you can make use of raster calculator. You can save your layer, temporary layer, by right clicking and then export save as, and you can give the location. I had saved it as DEM underscore greater than 1000, and you can save the file. and you can now remove the output temporary file. Now save your project in the folder solution under day 3, and now let me open a new project. Now I would like to work with Landsat 9 multispectral imagery collected over Pune region on 20th February, which I had downloaded from USGS Explorer. So you can load by from clicking layer. There are three ways. You can go to layer, add layer, and then add raster layer. You can select it. Otherwise you can um, go to the open data source manager, this button, which you can do by control L on your keyboard. Also you can open the data source manager, and here you can select the raster tab and browse to your location where you had saved your the multispectral bands B1, B2, B3, B4, B5, B6, B7 of Landsat 9 imagery. You can select all these TIFF files and then click on open and add to your layer panel. You can do the same thing from the browser panel. You can browse and then add them. Now at any point of time you can customize your interface. You can remove the browser panel if you don't want it. You can only just keep the layers panel as well as the map canvas area. Now you have these seven spectral bands of Landsat 9 um, loaded. You can check any one particular band by right clicking it and clicking on properties or double clicking the layer. You can check the information tab. Under information tab you will find the metadata. This is a GeoTIFF file. These are the statistics. As you can see, these are not actually reflectance value but scaled up values. So we have to apply a scale factor, I guess, but we are not concerned about the values of the pixel now. We will check other things like the dimensions, the origin, and then the pixel size is 30 meters. Um, Now it is no longer in degrees, and you will also find that the coordinate reference system is EPSG 32643 WGS 84, that is UTM zone 43 north. So it is a projected coordinate system. It is no longer the geographic coordinate system WGS 84 without any projection, where the EPSG code was 4326. So this the units are all in meters. Now this zone of UTM, you have to check under which the area of operation, under which zone of UTM your area falls, and you can choose the zone. Um, so and also so the coordinate reference system has been changed, and you can also find that your project CRS has also been changed to EPSG 32643. So what has happened is when you opened the new project and added the layers, by default what happens is the project will take the CRS of the first layer that gets added to the layer panel. So it has taken the 32643. You can change it anytime by from here. You can search for your EPSG code, like you can go back to 4326 by searching 4326 here, and then you can adopt it. But now we have we want to the it is in projected coordinate system, so let it be. We'll continue working with in the same CRS, which is more convenient to work in SI units if you want to do any calculations. For now, it is we are only concentrating on visualization and doing some band math on raster imagery. So you can now you have these seven multispectral bands added. Now let us see how we can generate various band combinations. Now in the initial lecture on remote sensing, you learnt about true color composite or um, the natural color composite and various. There will be only one true color or natural color composite, and there will be multiple false color composites. These band combinations, by taking three bands and giving them the red, green, blue colors, the primary colors, you can visualize and then you can identify the features on the surface of the earth, because in each band combination will highlight one particular aspect. So in that way you can identify or distinguish the features on the surface of the earth. Now let us try to do those band combinations and see the visualization. Now in the Landsat, the first band is aerosol band, and the band 2 is the blue band. B2 is the blue band, and B3 is green band. B4 is red band. B5 is NIR band. B6 and B7 are shortwave infrared 1 and shortwave infrared 2 bands. You can check the Landsat 9 documentation to read about the bands. So if you want to generate a true color composite, the you have to select B4, B3, B2, which are the red, green and blue bands of the electromagnetic spectrum. We have to give them red, green and blue channels. Then it will generate a true color composite. Now let us go to before doing that, now these are individual raster images. We have to stack them together before applying any symbology. For that you can go to raster option. You go to raster option, and then in the miscellaneous you can click on build virtual raster. Now we don't want to do we just want to create a virtual raster by stacking all the input layers, and then give the symbol change the symbology. Now you can click on this input layers and select all 7 bands, and then go back. So 7 inputs have been selected, and then you check this option of place each input file into a separate band, and now you click on run. So it will create a virtual raster, a temporary, as you can see, temporary layer has been created, a virtual raster, where it has selected the first 3 bands like band 1, band 2 and band 3. They have been selected and they were assigned green, red, green and blue colors in the same sequence. So some false color composite has already been generated by default, and you can see um, some but we don't know whether it will be of any use for identification of any feature. But let us first generate the true color composite. How you can do, you can right click this virtual layer, which is again a temporary layer only. Let it be. Right click it, go to properties, and then in the symbology, now the render type will be multi-band color. Till now we have been seeing single band gray and single band pseudo color, because we were dealing with elevation. Now we are dealing with multispectral imagery. Here you can select the bands B1 to B7 and then assign them to red, green and blue channels. So you know red band of the multispectral imagery in the Landsat 9 imagery is B4. So you can select B4, B3 for green band, and B2 as blue band. And simply you can rest of the things you can keep as it is. Stretch to min max. You remove the outliers by checking this cumulative count cut, or even you can select the min max and then you click on apply. So now you can see this is the true color composite. You can zoom in to your this portion is the Pune city, which is in bright the colors, means the reflectance in is more here, and you can see the vegetated portions also and bare land. Now let us zoom to this is the Kadakwasla reservoir, and this is the river, and the cyan color, gray color, you can see cyan color, it is the built up area. Now this is the true color composite, but it is of not much use to us. As you can see, it is just like what it appears if you are flying high above in a plane or in a from the top of the atmosphere. This is what it looks like. Fortunately, there is no cloud cover because this is the imagery from 20th February, and the sky is clear. But still, you can't make much out of it other than that you can see there is this greenery. These are the agricultural lands downstream of Pune city. This is the main Pune city, and these are the hills. But you can have better visualization or better identification of features using some other band combination, some other false color composite. Now let us try. Now let me give the NIR band, that is band 5 red color, band 4 green color, and band 3 blue color. Now you have seen it. This is the false color composite where the vegetated areas are which are having high reflectance in the NIR band, because it is given the red channel. The vegetated portions are highlighted in red, and there are different shades of red. These are the locations of cropped areas in the downstream of the city, whereas these are the locations of forested areas along the Western Ghats, which have bright tone of red. And here you have the croplands. You can even see the fields, but the resolution is only 30 meters. In case if you are using a finer resolution, you can better see. These are all the command. This is part of the command of many dams, like the Kadakwasla dam also. The canal it goes all along through the city, and here in the downstream of Pune we have the agricultural command. So this here, and one more thing, that you can identify is the water bodies in are very dark. So in the NIR band, water has high water absorbs more in NIR band. That's why they appear dark in the false color composite, in contrast to the vegetation. So this false color composite can be used for delineation of, say, the project or the agricultural and as well as the forested areas. Now suppose let us try with other band combinations. Now if you go for sphere 2 band and sphere 1 band, that is B7, B6 and red band. If you select these three bands, 7, 6, 4, this combination can be used for identification of urban or built up area. Um, Now, these are the various band combinations you will find in literature. I'm just implementing them, which are already known. So you can select the virtual again, double click the virtual layer. You go to red channel. You have to give the sphere 2, that is band 7, and green channel you have to give sphere 1, that is band 6, and in blue channel you have to give the red. Now don't get confused between red band and red channel. Red band means it is the range of electromagnetic spectrum. See, the visible range of the electromagnetic spectrum is from zero point 0.4 to zero point 0.7 micrometers. So it starts with the blue band from zero point 0.4 to zero point 0.5 approximately, and then from zero point 0.5 to zero point 0.6 micrometers it is a green band, and then from 0.6 to zero point 0.7 it is the red band, and beyond that we have the near infrared band and thermal infrared band, and so on. You will have the microwave region. On this side, uh, next to blue we will have the ultraviolet region, and then the wavelength will decrease. It will goes up to gamma rays, X-ray, the gamma rays, and so on. So in the optical remote sensing, we make use of the imagery collected in the optical bands, that is the visible band and the infrared, near infrared and thermal infrared band. So these are the bands which are there. B2 is the blue band, B3 is the green band, B4 is the red band, B5 is the NAR band, B6 and B7 are shortwave infrared 1 and 2 bands. So, and once you this range of the wavelength is given, the red range of the wavelength electromagnetic spectrum, if it is given the red color, green portion of the electromagnetic spectrum, it is given the green color, and blue band is given the blue color. It will be a true color composite the way your eyes are visualizing. The sensor is capture. If you see any single image, as you can see, any single image will be in the gray color scale only. Uh, Now this is the red band. If I display only the red band, it will not be in red color. In that red region of the wavelength, which is having a range of the wavelength, every feature will be reflecting. If it is reflecting on the surface of the earth is reflecting, if it is reflecting high, like the bare soils will be reflecting high in the red region, so they will be appearing brown or red in color. So they will be brighter, like you can see in white color, whereas the water, it reflects very low in the red band. That's why they are in dark color. So it is only a grayscale only. Individual bands will be in the grayscale. However, if they are given the RGB channels, then you will see the true color composite and various other band combinations, false color composites, which will be useful for distinguishing the features visually. You can make use of digital image processing for doing it digitally. You can identify the spectral signatures of individual pixels, and then identify the feature. You can assign the land cover that we will see when we come to the land use land cover mapping. So for the time being, we are seeing the band combinations. So we have seen the true color composite, we have seen one false color composite. Now we want to do the false color composite by assigning sphere 2, sphere 1, and the red bands to red, green, blue channels, which will be useful for identification of urban areas. So you can see the urban area of the Pune city you can is prominently you can identify as distinguished by the surroundings. Now, if you want to identify the agricultural fields, there is a band combination of SWIR 1 and then NIR and then blue band. So let me select SWIR 1, NIR near infrared, and blue band, that is B2. With this band combination, it it is possible to identify the agricultural lands. See, these are the portions. You can see the different tones of green for forest and as well as agricultural regions. In the downstream of the city, you can find even the field boundaries. Also, you can notice at 30-meter resolution. You can see the agricultural region. So this band combination is useful for that. Now, if you want to have clear distinction between land and water pixels, you can have the combination of NIR band, then SWIR 1 band, and then red band. You can select it. NIR, that is B5, then SWIR 1, that is B6, and then red, that is B4. And if I apply it, you can check by zooming in. You can uh, have clear distinction between the water and land pixels, which will be useful for delineation of water bodies. So that is about various band combinations, various false color composites. Now let us try to uh, do some band mat. Let us try to implement using the raster calculator. Uh, we have the NIR band and red band with us. We can calculate NDVI value for each pixel by implementing the formula of NIR minus red divided by NIR plus red, which will give you the normalized difference vegetation index, which varies from -1 to 1. If it is greater than 0, that means it is vegetated pixel. Forest will be having high NDVI, croplands will be having high NDVI but less than forest areas, and the water pixels will be having NDVI around -0.01. Let us implement it by going to raster. You can use raster calculator from here now, or let us use it from processing toolbox only. Under raster analysis, you select the raster calculator, and here you have to write the expression NIR, that is you double click B5 minus B4, that is red band. You close the parenthesis, divided by again B5 red NIR band plus red band. You close the parenthesis again. So the expression is valid. It is a predefined expression, is already there here anyway, but doesn't matter. You can check the reference layer for automated extent, cell size, and CRS. You can give any of the band which have all of them have the same extent, cell size, and CRS, and you keep others as it is. We can save the output to file, otherwise it will only create a temporary layer. You go to the solution folder of day 3 and then give the file name as NDVI, and then you run it. So once it is done, you will see that a new layer has been added. You bring it to the top, NDVI. It is a permanent layer. So you can see this is the NDVI layer. You can zoom to the full extent. For every pixel of the Landsat 9 scene, it has calculated the NDVI. You can check the values by this identify features. Wherever the value is very less, it will be in dark in color, like these all water bodies. As you can expect, the values are around minus 0.01 to minus 0.06, minus 0.05, so on. Now, even though the reflectance values here are not, if you check the original any of the band, the values are not uh, ranging from 0 to 1. They are in scaled up values, but because the NDVI expression has the bands in both numerator and denominator, it is giving you the correct value of NDVI ranging from minus 1 to 1. It is, the scale factor is getting cancelled in numerator and denominator. So you can check, you can add the base map. Let me add the base map of forests, Google satellite, Google satellite, and let me check the NDVI value for forested regions. Let me deactivate all these layers and let me keep only the Google satellite imagery. So these are the forested areas in the Western Ghats. You can check the NDVI value by activating the layer and then clicking identify features. So you can see the NDVI value is about 0.3, 0.4 wherever there is thick vegetation. If you see the agricultural lands in the downstream, here NDVI value is also high again, but somewhat less than the forests. Average NDVI will be slightly less than the forests, if you see. So you can do this way. Now let us try to implement NDWI. As you may be knowing, normalized difference water index, it makes use of green and NIR bands of the multispectral imagery to calculate normalized difference water index for each pixel, and wherever NDWI is greater than 0, we can consider it as a water pixel. The threshold where the land pixels end and where the water pixels start, that it varies from scene to scene. In general, it will be around 0, but for the thresholding, we need to use automatic, because from person to person, if you are doing the manual thresholding, it differs from person to person. It will be become subjective. Whereas if you go for OTSU automatic thresholding, you can have you can decide the threshold in a better way. Now let us implement first the NDWI, which is green minus NIR by green plus NIR. So you can again go to processing, toolbox, under raster analysis you can select the raster calculator, and here you can again write the expression. Here you have to select green band, that is B3, and minus NIR band, that is B5, divided by again parenthesis B3 plus B5. And then you can give the reference layer. You can check any of the bands, but not the Google satellite, which is in a different projection system. As you can see, EPSG 3857. So it will list out all the active layers. which are in the display panel, in the layers panel. And then you will select the save to file. You can save it as ndwi, save, and then click on run. So once it is done, you can zoom to the layer. So you can see now the water bodies are in appearing bright. That means the values are high. This is again a single in the grayscale. Wherever the values are high, it will be in bright in white color. So you can check the values in water bodies. It is greater than 0 in general, 0.12, 0.13, and whereas in the land, the NDWI land pixels will be less than 0. So let us assume here the threshold is 0 without going uh, into the details. Now let us try to uh, map the water bodies and mask out all the other pixels with NDWI less than 0. That you can again do using raster calculator. You go to raster calculator again, and now you select the NDWI layer. You double click it, and you have to write an expression such that so you can select wherever the NDWI is greater than or equal to 0. You want to retain the value of or you want to have the value 1. So if you run this expression, simple expression, NDWI wherever it is greater than or equal to 0, for every pixel this expression will be evaluated, and wherever it is holding true, the pixel will be assigned the value 1, and wherever it is holding false, the it will be assigned the value 0. That is a boolean layer will be generated. So here instead of writing any complicated formula, I am simply writing this expression, and I will run it without saving. I can give the reference layer again any of the bands and then run. So a temporary layer will be generated as an output, where you can see, you can identify using the identify features. The water bodies will be having value 1, where NDWI is greater than or equal to 0, and rest wherever it will be 0. Even the small water bodies, this is the pixel, these are 30 by 30 meter pixels, where you have small water bodies. Again you will find the value to be 1, and surrounding it is 0. Now if I want to mask out the values of 0, you can go to uh, output, properties, go to transparency, and then add additional no data value. You want to mask out and you want to make them transparent, so you can add 0 as the additional no data value, and then you apply it. You zoom to the layer, you can see, and let me deactivate all other layers. So you can see in this temporary, this is still a temporary layer, where the wherever water bodies are, it has the value 1, and wherever there is no water body, it has no data. No data means it will not be considered for any analysis. It is masked out. So you can change the symbology. You can simply give the color, change the color. Now here there are unique values, so you can change the render type. You can select paletted or unique values, and then classify. There is only one value 1, so you can give the color by double clicking. You can change the color. and then you click on apply. Zoom out to the extent so you have mapped the successfully mapped the water pixels. Now you can further sieve it, do the sieve analysis to have the continuity, all those things. Now this is not an very foolproof method because NDWI value, it is subject to the the cloud cover, atmospheric disturbance, all those things are there. So but still you can have a very reasonable way of delineating the water bodies. You can activate the Google satellite and check your water bodies. So this is the Kadakwasla reservoir. Even the small water bodies within the city, they have been delineated. So that's all for this session on working with raster data. We have seen how we can load raster data, single band raster data, that is digital elevation model, and then we have seen how to change the symbology, and we have also tried to load the multispectral imagery and how to use raster calculator to implement various band combinations and also indices such as NDVI and NDWI. In the next session, we will do some basic vector analysis and raster analysis. So thank you very much.